Hello ladies and gentlemen, today we're going to talk a little bit more about graphing quadratic functions. However, today we're going to get into translating, reflecting them, and things of that nature. Now you did this already with absolute value graphs earlier in the year, and you'll notice that the rules are the same. So if you pull out your absolute value graph notes, you may recall absolute value graphs look like the letter V. So let's call it a cousin to the quadratic functions. The rules for transforming them are the same. So let's see, graph y equals x squared. That's our first directive here. So let's see, we'll get x squared in here. X squared, we'll take a look at the picture. Okay, that's zoom standard, which gets us that picture. Let's move it over here, and then you can take a look at it. Alright, so y equals x squared has a turning point at 0, 0. The axis of symmetry is x equals 0. Graph the following and describe the movement of the quadratic. Now, if I go in here and add 3 to the end of this, plus 3, graph that, you will notice that there has been a shift. Let me just move this down here. So the question is, what happened to the shift? And if you look at it very carefully, you will notice in here that we have moved up, smallest curly bracket ever, 3 units. So the effect of plus C on here is going to be to move up C units. So if I add a number to the end of the quadratic, it's going to move me up that many units. Now if I go back in here and turn this into minus 3, so I'm just going to replace the plus sign with a minus sign. We take a look at the picture, and perhaps you can predict the result, and you can see it here. Now we are going to move down, and then same deal, 3 units. So down 3. So minus C moves us down C units. Alright, we're changing things up here, so up and down, adding a number at the end. You'll notice in our next two examples we have parentheses introduced. So I'll actually clear out this, and I'm going to put my x plus 3 in parentheses, and then I will square the whole thing. Make a guess. This is actually going to surprise you. It doesn't do what you think. And you'll notice that the graph has been moved, and probably not the direction that you predicted. In this particular case, we're going to move to the left. You'll notice the whole thing kind of occurs a little bit sooner. That's what plus 3 does. It makes every point happen 3 units sooner. So this is going to move you left C units. In this case, 3 units with the example we have. Well, if the same relationship holds that we noticed in the first two examples, plus went up and minus went down, plus goes to the left, minus should go to the right. And if we take a look at the picture, you do see that in fact the minus goes to the right. So we're going to move to the right. C units. This is going to take some memorization because the plus 3 moves left and the minus 3 moves right, and that's not what our gut instincts tell us. I have minus 3 inside the parentheses, and I'm going that way 3 units to the right. Alright, that will have to be memorized. There's no guessing on that. Although, of course, with a little calculator play, sometimes you can answer these for you. Reflection. Now, short for reflection, the short way of saying it is a flip. I'm going to flip the thing over. So if I take my original x squared here and just put a negative sign in front of it, once again, that's not a subtraction sign, it's a negative sign. I'll get an error if I put a subtraction sign there. Take a look at what happens. It goes from a happy face to a sad face. Now, we saw sad curves yesterday. This is going to reflect over the x-axis. Alright, and actually that's not 100% accurate, but in this particular graph that is true. It is going to flip over the turning point, and we can talk a little bit more in class about what that means. But if the original graph is up here, so say I have this graph, which is y equals x squared plus 3, all right, and then I take it and say, well, we can play with it in a number of different ways. So if I go y equals negative x squared plus 3, then what you're going to see here is it's going to flip over from this point, so it's going to look like that. All right, so if I just change that sign, and we can do that on the calculator, and you can verify it this way. So like I'm checking my answer, plus 3, and then you graph it and you can see it's going to flip over, but it's going to be moved up, all right, because the plus 3 moves it up. So these things can kind of combo together. In this case, I would reflect it over the x-axis first, then I would slide it up. All right. So rules for transforming: a transformation slides you around, so up, down, left, and right, and reflection flips you over. All right, scaling. This is a little bit difficult to kind of understand without looking at the table of values, and we do not want to waste an enormous amount of time with this. But remember that you're taking x squared and then you're multiplying it by 5 here. That's going to make the thing take off faster. All right, it's like a rocket with more powerful fuel in it. So as you can see, here is y equals 5x squared. And on the same xy axis, I'm going to make it darker, but I will graph x squared with it. So there's x squared, and then I'm going to go all the way over to the left. You notice the blinking cursor on the left. I'll hit enter, and there's a fat version of that. So take a look. So you notice 5x squared is going to rise faster. So the sides are steeper. It rises faster. You might be able to guess what 1/2 is going to do. Based on that, kind of the opposite. But if I do, and remember in parentheses, 1 divided by 2, and then my x squared. We graph that. And remember the dark one is y equals x squared. So you'll notice that 1/2, because it's less than 1, see here, see between 0 and 1, because it's between 0 and 1, it's going to be a little bit flatter. So the sides are flatter. It rises slower. All right, so those are all the rules. Scaling. So you're going to really have difficulty if a is something other than 1 or 2 to get that on a piece of graph paper. You'll have to judge where you want to put your axes based on that. Because, you know, like 3x squared, boy, those values are going to grow quickly. When I say those values, I mean the y values. If I plug 3 into 3x squared, x squared is 9. 9 times 3 is 27. So 327 would be a point you'd have to plot. Boy, oh boy, that's growing very quickly. Alright, here we want to graph it, find the vertex, and give the axis of symmetry. No information has been given here to help us. So what we're going to do is go with the axis of symmetry first. A equals -1, B is equal to -2, C is equal to 5. And the axis of symmetry formula is x equals -b over 2a. Well, that's -2 over 2 times -1, which is 2 over -2. So in this case, x equals -1 is the axis of symmetry. That's important because that's the middle value of my table. So -1, I got -2, -3, -4. So 3 points on one side of it, 0, 1, and 2. And we want integer values. So that's my x column. I'll use the technology to give me the y column. So we can go in here, clear out our two graphs. Negative x squared minus 2x and plus 5. Take a quick look at the picture. It's always a good idea to know what you're getting yourself into. Hit second and table. These are the table of values we wish. -1 has to be in the middle. I already have that. So I can slide this over so that you don't have to watch me flip back and forth a bunch of times. But this has to get translated to my paper. You cannot get full credit for a graph without 7 values listed in a table. No table, no perfect score. And this certainly, you have technology doing it for you. So why on earth would you not, want to go for that perfect score? So there we go. There's negative 1, 6. We have 0, 5, and negative 2, 5. We have negative 3, 2. And we have 1, 2. And then finally 2, negative 3, and negative 4, negative 3. We're graphing the entire thing. We know that because they did not give us integral values. So we're graphing the whole thing. We put arrows on there. We go back and label the points. Negative 1, 6, 0, 5, 1, 2, 2, negative 3, negative 4, negative 3, negative 3, 2, and negative 2, 5. And last but not least, we put the equation on here. Y equals negative x squared minus 2x plus 5. So A is done. B says find the vertex. The vertex is another word for the turning point. So our vertex is negative 1, 6. And the axis of symmetry we found at the very beginning, x equals negative 1. And that problem is done. Alright, moving on. Write an equation that represents the parabola shown in the accompanying graph. Well, you will notice that the origin is right here. So this has been moved 3 units to the left, and we know to move 3 units to the left we do x plus 3 squared. It has also been moved up 1 unit, so we put plus 1 on the end, and that is how boringly easy it is to do that. You just have to know the rules. To the left is plus inside the parentheses, and up is plus at the end. Find the vertex and line of symmetry. Well, as you can see here, we have a maximum right here. And if I take a look at that point, reading it off the graph, that's 1, 4. So 1, 4 is our turning point, and that is another name for the vertex. Alright? So vertex is 1, 4. The axis of symmetry comes right off of here. I don't have to do a computation. That value, if I set it equal to x, is the axis of symmetry. If you know the turning point, you know so much stuff about this equation. It's kind of ridiculous. It's all hidden in there like a code. A small rocket is launched from a height of 72 feet. The height of the rocket in feet h is represented by the equation h of t is equal to negative 16t squared plus 64t plus 72. T is time. So h of t is the height given some time. We want to graph this equation on the accompanying grid. Use your graph to determine the number of seconds that the rocket will remain at or above 100 feet from the ground. Only a graphic solution can receive full credit. So we are going to graph y equals negative 16t squared plus 64t plus 72. H of t, which is this symbol right here, means the same thing as y as far as you are concerned. It's a little bit more sophisticated notation, but it means the same thing. The problem we're going to get into here is this is a real life question. And a real life question doesn't really live between 10 and negative 10. So we're going to have to play with the grid a little bit. Time can't be negative, so there's no reason to have negative on our axis at all. And we have to account for the fact that our graph is going to be pretty darn tall. So our table of values is going to start at 0 for sure because this is a real life question. Alright, so we're going to have a t column and then we'll have an h of t column, which is the same thing as y. So here we go. First thing, let's play with our window a little bit. We do not have to have anything negative, so we can set x min equal to 0, and once again I hit the window key. If you look, you can see it turning red as I'm hitting it over and over and over. X min is 0. We're going to make y min 0 as well. And if you take a look at the graph, you're going to see this. Now, the problem is that the graph is taller than 10. So we're going to play a little bit. 72 is C, and that is where it crosses the y-axis. So I think we're going to make our y maximum a little bit larger than 72, and I am guessing right now 120 is what I'm going to try. I don't know if that's right, but look, it's a little too low. At least I got my head wrapped around the problem now. Hit window again, and I'm going to turn my y max into, what do you think? Do you think 150 fits? Let's see. It's trial and error, so I might be wrong. But there we go. We can see the whole graph in here. We want to graph it until it hits the bottom, and you can see that it hits the bottom. Oh gosh, maybe around 5 or something like that. But let's get this. Take a look at this. So we hit second and table. We want to start with t equal to 0, but we want to kind of graph it until it hits the ground. So we want to figure out where y is going to be 0 as well. And you notice it doesn't appear perfectly on the graph. That's disappointing, but we'll survive. So we got 0, 72, 1, 120, 2, 136, 3, 120, and 4, 72, and then 5, negative 8. Obviously, I can't go below the ground, so I can't go down to negative 8 there like that, but at least will give me the ability to figure out where it does in fact hit the Earth. Alright, once again, this is a small rocket being launched from 72 feet up in the sky. So this represents the starting point, that's the y-intercept, and then it flies through the air for a few seconds and hits the Earth. Alright, so now we're going to graph this thing. I'm going to put 0 right here, and I think I might be able to count by tens. So 0, that'll be 10 here, 20, 40, 60, 80, 100, 110, I'm sorry, 120, 120, 140, and 160, and the tallest point is 136, so I'm better than that. And now of course I got negative 10 down here. Okay, so we just start plotting these points. 0, 72 right there, 1, 120. So how do we want to put our ones in here? As you notice, we only have to go up to 5. So how about we just go 1, 1, 2, 3, 4, and 5. You can spread out a little bit if you want to. You see we have more grid available. So 1, 120 puts us here. 2, 136, so that's about, say right there, and 3, 120, 3, 120, and 4, 72, so let's see, 4, follow it up to 72 here, and then 5 is negative 8, so that's going to be, this would actually be negative 20 if I did it accurately, so let's fix that. Negative 8 is probably about right here. Okay, and keep in mind this is where the Earth is. That's the ground. There's a little hill. On accident, I drew a little hill. Alright, so we draw our graph. Boom, boom. That's the flight of our rocket. And we can label these points. 4, 72, 3, 120, 2, 136, and we got 1, 120, and we have 0, 72. Now, what's the question here that we have to answer? So we have the thing graphed, and we can put the equation on here. Y equals negative 16t squared plus 64t plus 72. And finally, it says use your graph to determine the number of seconds that the rocket will remain at or above 100 feet above the ground. Okay, so we're going to graph the line representing 100 feet above the ground. So if you take a look right here, this is 100 feet above the ground. Where does it happen? It appears to happen here, which is at 0.5 seconds. And it stops, and it intersects pretty good, even with my little sketch here. Because, of course, the sketch is never going to be perfect. 3.5 seconds. So to figure that out, we can do 3.5 minus 0.5. It's going to be at or above that position for 3 seconds. And that's it. Now, for bonus points, can you tell me the equation of this line? I'll look for it in your notes tomorrow. This green horizontal line, what is the equation of it? Remember, all horizontal lines have an equation that kind of look the same. That's our lesson. Have a wonderful evening. I look forward to seeing you. Enjoy your long weekend.